opened microphone. Jean-Luc, you didn't open. Yeah. Okay, let me introduce. Today, let's start today's seminar. Today's speaker is Professor Tobias Ekholm from Uppsala University in Sweden. The talk title is Skein Valued Curve Counting. Please welcome.
Okay, thank you. Thanks for the invitation. Great pleasure to be here. So I planned some kind of a little bit board talk, so I'll try to do that on my iPad. So also that's so that I can adjust things. So please feel free to interrupt me whenever there is something that you would want to know more about, or if you already heard, I can kind of go on faster. Anyway, my plan was to talk about first some kind of introduction to the topic at all. So that's a comparison between closed curves and open curves and what actually happens. And then talk a little bit about this connection between Homfley-Skein relation and curve counting for Lagrangians in Calabi-Yau 3 manifolds, and then apply the resulting theory a little bit. So in particular, you get some kind of Skein recursions that allow you to sometimes completely determine holomorphic curve counts in terms of Homfley polynomials and so on. So that's this kind of famous Oguri-Alpha conjecture, and we'll see if I go further, then I'll go further. So anyway, let me start. So I want to start with the symplectic Calabi-Yau threefold. So what does it mean? It means that there is a kind of symplectic form omega, sorry, we fix also an almost complex structure J, which is compatible to this omega, and this almost complex structure gives us homotopically unique kind of complex structure on the tangent bundle, and this Calabi-Yau condition is that the first Chern class of this complex bundle is 0. And then inside this X, we will take some Lagrangian submanifold. So this just means that omega restricted to L is 0. And, and we will, in kind of parallel with this Calabi-Yau condition, we'll say that the Maslov index of L is 0. So how to think about this Maslov index? So it's the following. So in this case, so if we have this X, it has first Chern class 0, so it has trivial determinant bundle. So in this determinant bundle, we can trivialize it. It's a complex line bundle. And our Lagrangian, which I should have said, we assume is orientable. Then this real orientation of the Lagrangian determines for us a real line in this complex line bundle. And if we walk around some one cycle inside the L, then we have a rotation number of this line inside the complex line, and we require that corresponding homology class is 0, or cohomology class. Okay, so in general, we could also, and I'm going to write some dimension formula soon. So in general, we could think about same kind of setup where we have a manifold in dimension 2n, which is symplectic, and we have an n-dimensional Lagrangian. And so what we are going to do, we are going to look at holomorphic curves. So in other words, we take maps from a Riemann surface with boundary into this X boundary on L, and we are going to look at solutions to the d bar equation. So d bar of u, which is just a Cauchy-Riemann operator. So little j here, this guy is the complex structure on the surface, and we require this is 0. Okay, now this operator is elliptic operator. So there is some kind of Fredholm index for this one, which allows us to determine the dimension. This is some kind of famous Riemann-Roch calculation or index formula, and it says x, then the dimension, local dimension of nearby solutions, where we allow the domain to vary conformally, not conformally, we allow the J to vary on the surface and the map to vary. It is given by the following formula. So n here is the dimension of X ambient manifold is 2n. So it's n minus 3 times the Euler characteristic of the surface plus twice the relative Chern class of X and L evaluated on the map U. Okay. And now in our case, this n, we have n is equal to 3. So this term goes, and this kind of C1 is equal to 0 and Maslow is equal to 0 implies that this term also goes. So for us, all the holomorphic curves that we see, independent of Euler characteristic and independent of everything, the dimension. So this kind of Calabi-Yau threefold and Maslow 0. No, Maslow Lagrangian is 0 implies that this dimension is equal to 0, right? For all kind of curves. So one could imagine that therefore that we could count these curves. So curve count, we can hope for a curve count, and so we take M to be the moduli space of holomorphic curves, and then basically something like this. So if you take this sum over all these maps in M, and say in Grom-Witten theory, you count them by, maybe I'll just write like this. So we count them maybe by their homology class, and we weight by area and so on. So this is, of course, an infinite sum, but if you restrict the homology class, this is kind of finite. So it's filtered and nice. So now let's think a little bit about closed curve counting. So by closed, I mean no boundary. So in this kind of string theory lingo, so open will be open strings with boundary, and closed without boundary. So now if we want to count such curves, well, or maybe so again, as I said, if we assume we can perturb, this is a kind of big industry, how do you actually perturb the d-Bohr equation to get transality? But for now, let's assume we can do it. And if we perturb it, then this is sort of sum of over an zero-dimensional manifold, or maybe better to say orbifold. So each point, each curve in there counts with some rational weight. And then we sum them up, and we get basically a number times homology class. And we like that number to be invariant under deformation. So in particular, we did choose some complex structure, maybe choose some perturbation, and we'd like it to be invariant. And because of that, we study sort of one parameter families of deformation. So and we'd like to see if this count has a chance of being invariant. And indeed, it has a chance of being invariant. So let me think of this deformation parameter. So this t, I call it, and I start at, say, t equals 0, and I want to end at t equals 1. So here at t equals 0, I have my moduli space M0, and here I have my moduli space M1. And that moduli space, maybe I should use some color or something. That moduli space is just a bunch of points over here at 0.
Excuse me, if we have a one-dimensional deformation for a moduli space, can we study it as a sort of braid group? So if we have points if we have a moduli space, we move points, we go through something of codimension 1, and maybe it can be studied in a way similar to braids. So we have
Yes.
such a
Yes, we can. This in some sense even simpler. So now we're just going to study it as a one manifold, actually, as a one manifold with boundary, and then we're going to show that there's sort of no strange boundaries, and therefore the count will be invariant. So this is in some sense at this point, of course, setting up the theory maybe not that simple, but at this point we're much simpler than braids. So we're just looking at the abstract one-dimensional manifold now, without any embedding anywhere. So it's a little bit simpler than braids. So braids also keep, I mean, then you have this blue thing that I'm going to draw embedded into some three-dimensional space, but here it's just an abstract space. So so these blue guys is some zero manifold or maybe zero orbifold. Okay.
okay.
Yep. So then over at M1 we have some other points here, and if we look at the family of solutions, one would expect that they form a one manifold, oriented one manifold, and if they really do, then of course the count over here will be the same, right? So as the count over 0 will be the same as the count over 1 because we have this oriented cobordism connecting them. So this is kind of almost true if we knew that this one parameter, if the one parameter family of solutions was smooth, and then somehow by this Gromov compactness, this is almost true. So what it says is that moduli space, this moduli space is compact manifold up to bubbling. So there is one thing that we have to care about. And so in principle, maybe this is not quite the case, but we have to worry about something like this, where some moduli space come in here and then maybe just ends in the middle. And we know if it happens, how it happens, and it would happen like this, that we have this holomorphic curve, and I'm drawing it like here now. So we are closed curves, and then this this region in the curve pinches, and in the limit something kind of bubbles off like that. So there is sort of no other way that this compactness fails. So a smooth curve can converge to nodal curve, and that would be kind of, if this happens really, I'm going back, if this happens, so this is maybe this nodal curve, here is a smooth curve, that's really bad for our count, because then we stop in the middle of the deformation parameter, and the count wouldn't be invariant. But you see, this nodal formation has a kind of a, the node, so an interior node. It's modeled by basically something like x times y is equal to epsilon, where this epsilon is a complex parameter. Or so this is sort of one way of thinking about it. The other way is, if you think about this thing, then you have this portion here is a growing neck. One part of the curve is over here, another part of the curve is over here, and when you break, you go kind of all the way into two neck regions which are infinitely long, and when you want to glue them back, then you have two parameters. You have the length, maybe I call it rho, and you have the angle theta to glue it back. Or so those are somehow, if you take the exponential of rho and theta, rho plus I theta, whatever it is, then you get this epsilon. So the key point here is that since this is a complex parameter, bubbling is a codimension 2 phenomenon. In moduli. So that means that if I now kind of step back, that means that this one is not going to happen. Sorry, this one is not going to happen generically, because it's the same thing as, you want to go from this, whatever it is, blue point 0 to this blue point 1, and you have some bad thing happening at the origin. But of course you can then just do what we always do when something like that happens, we go around. So that means that choosing somehow this data, this one parameter data generically, we actually do find this cobordism of moduli spaces, and the count is invariant. So therefore, in some sense, we have this Gromov-Witten theory which counts this, and then it doesn't depend on choice of perturbation, choice of complex structure, and so on. So this is codimension 2 in moduli, and that implies that that somehow count is deformation invariant. Okay, very good. So now let's move to the real case, or real case, the case of with boundary. So now, so repeating. So now consider open curves. So again, we can take this dimension. The dimension of M, as we saw, was 0. So we can again try to do this curve count. And we can see whether now it is still invariant. Well, we have the same kind of picture that we had before. We have this kind of time parameter, and we have the blue person was here, M0, M1. But now, indeed, there are some kind of cases like this. So this cannot be avoided, and let's see why. So here cannot be avoided. So that's because when we have curves with Lagrangian boundary, then the same kind of phenomenon that we saw before should now be drawn with boundary. So we have some kind of interesting curve here, and it converges to a curve with a real.
Excuse me, what can be avoided?
So I'm explaining now what cannot be avoided. So these nodal curves that could appear in breaking. So there was this kind of Gromov bubbling. So that such nodal curves cannot be avoided in one parameter families. So that means that this moduli space that we're following, it has some interior boundary, and therefore this count here jumps.
Okay, but maybe we can do something like that. We can put some generators for codimension 1 and look for relations for codimension 2. Try to write a word similar to a braid word. So if we go from M0 to M1, maybe we will be able to write a word corresponding to this coordinate.
Yes, we are going to do something like that, but it's going to be in some sense even better. So let me explain first why there is this interior business. So now the model again is xy is equal to epsilon, but this time, of course, epsilon is a real number, right? So because the boundary here is supposed to be in maybe R2 then. And so you take half of this curve, so epsilon kind of, this is our favorite high school thing, right? So we have this curve, and it's converging to these two lines, right? So this has now codimension 1 and cannot be avoided. And on the other hand, there is another such instance, which is, so because we're doing real stuff, there is the other model, which is x squared. Maybe this is better to write as x squared minus y squared. X squared plus y squared is equal to epsilon, right? So then we have some kind of boundary in some curve, and it's shrinking away, right? Sorry, maybe I'll remove this codimension one. And it's shrinking away in the limit. So when this is epsilon is equal 0. So we have these kind of two phenomena, which happens for real curves and which have codimension 1. So what it means is something that in some sense well-known problem. So if you have, if I'm going to fill this one in a certain example, you can imagine that you have two holomorphic disks here, right? Which I shouldn't imagine anything like that, but maybe I just say this. So here we have this nodal curve, and over here we have just one curve, and that's a kind of disaster for our count, right? So it means that the count will jump. But we can also study these instances, and what we will find is exactly the Skein relation of kind of quantum topology. So let me now switch gears for a little bit, and I'll come back to this picture in a second. So let me review what is the Skein module. Skein module. Module of three-manifold. And for us, the three-manifold will be the Lagrangian. So this Skein module of L is a module over a ring, which is somehow two variables, A and Z. And then the generators are so isotopy classes of framed links in L modulo three relations that I'm now going to give you. So first relation is the following. So you have some link, framed link in your manifold, and we think of it as having blackboard framing. So take the normal vector field in the projection that I'm drawing. So this one is equal to Z times this guy. So what I'm talking about now is that we have two links that look exactly the same outside of a small coordinate ball. Inside this coordinate ball, we have three possibilities of changing it, right? So, and we impose this relation. So this is the first Skein relation. The second Skein relation is that it basically, in knot theory literature, called normalization of this unknot. So we have in a coordinate plane, coordinate ball, a small curve line living in a plane inside this ball, and then the value of this this is equal to just something in the ground ring, which is A minus A inverse over Z. And third is this kind of framing relation, which says that if you change the framing, so this is equal to A times that one, and if you have the other one, it's an A inverse, but maybe it's enough to write this. So this is some kind of Skein. This is the Skein module. Where does it come from? It comes from follow up on Jones polynomial that Jones defined in the mid-80s, and then was generalized to this Skein, to this Homfly, I should say, Homfly. So Homfly Skein. And these are some actually, 8 authors. So 3 teams of pairs of authors, and another pair that somehow added on later did the same thing. So it is a very straightforward in some sense, or a natural generalization of what Jones did. He found this kind of Skein relation. Anyway, for S3, for example, which was the case that everybody studied in the beginning, this three-dimensional sphere, or maybe R3, then you see that if you have any link and you have these moves, you can actually remove all the crossings until it's only unknowns. And therefore, in S3, this whole module is actually reducing to the coefficients, and if you have a link, it's equivalent to its Homfly polynomial. But as we will see later, in examples at least, if you take something like solid torus, then by results of Turayev, this Skein module actually has infinitely many generators, so one connected curve in each homotopy class, positive and negative, and their products. So it's a huge thing, and it depends a little bit. It's different depending on whatever manifold you have, but at least for simple manifolds, we know it. For all manifolds, certainly not. There's stuff in the chat. Does it? I don't see the chat. That's strange. Okay. So if you want to ask me, just shout out and I'll try to answer. So I have some trouble with the chat. Okay. So this is the Homfly Skein module of a three manifold. And now we're going to check that these wall crossings that we saw, they kind of exactly correspond to the Skein relations. So let me now take this kind of draw the same picture that I drew before. So I'm going to draw on top here the deformation parameter, and then I'm going to draw this bad scenario, one of them, where I had this moduli space which just ended. And here I'm going to take the hyperbolic version first. So hyperbolic. Then what did we have? We had a curve that somehow looks like this and ends in a curve like that, right? So this was this xy is equal epsilon. But now observe that this curve here is actually, you can look at its normalization. So instead of looking at it as a nodal curve, you can basically forget these marked points and let it just move as it wants. And what one can show is that there is another moduli space here, which is the moduli space of that curve thought of as Euler characteristic 1 higher. So here's the same picture in the middle here at this green point. So the same time. But then when you think about these kind of generically moving thing here, maybe I should draw it with the right kind of crossing. Then it crosses through here. So now you see we have this option of saying that if we impose the relation 1, then impose relation 1. So that said that this one minus that one was equal to c times that one, and count u as by z to the minus Euler characteristic of s. Then you see that this moduli space here is some moduli space of Euler characteristic chi. Perhaps this moduli space is Euler characteristic chi plus 1, right? Because we add one handle to go from one to the other. And you see that if we impose this relation, we count the curves by their boundaries in the Skein module of L, then we cure this wall crossing, because on this side here, on the left-hand side, we count this guy, we count this guy and that guy, and on the right-hand side, we count this guy. And if we say that they are equal, then we cure the wall crossing. There is no change if we go from left to right. We remove this bad point. So the elliptic version, maybe I'll draw it in red, is exactly the same. So now we have some curve here, and in the middle here, we have this curve that intersects the Lagrangian. It can be viewed as normalization, and it again comes in a one parameter family, which is a little bit hard to draw. But if we think about it, this curve is a two-dimensional object intersecting a three-dimensional object in a six-dimensional space. So if it moves generically, it's exactly like crossing through. So 2 + 3 is 5, intersecting at this magical moment. And in codimension 1 family, it's kind of crossing through. So what we would like to do is we would like to count, in order to cure this, so count US by A to the linking between U and L. So this is, of course, a little bit tricky to define because U has boundary on L, and if you want to define the linking number between two things where one has boundary on the other one, that's a little bit tricky. So I'll tell you how it goes, and it leads also to the third Skein relation. But if we can make sense out of this linking, then note that somehow here we find exactly A minus A inverse. So here we have kind of plus linking, here we have minus linking. So this is A to the 1 minus A to the minus 1 is equal to C times this unknot that sits there, right? So again, in the same way, if we count the curves by boundary in the Skein, make sense of this linking, it will stay invariant. So let me now tell you how to make sense out of this linking. So how to measure linking. So what we do is we find the four-chain, we assume that this one exists. So in examples, it will be clear. So four-chain C, such that the boundary of C is equal to twice L, okay? And here is L, and along L, we fix a vector field, that's xi, and we take this chain to start out to be smooth near the boundary and start out one branch of it as plus jxi and the other one as minus jxi. So xi is vector field, maybe take it non-vanishing, generic is good enough, but let's take it non-vanishing for now. Multiply it by j, then it sticks out of the Lagrangian, and continue it a little bit. That's the beginning of a four chain with boundary on L, right? You can go one way and the other way, and we orient the two pieces in this weird way that they don't cancel, but the boundaries becomes 2L, right? So that's this equation here. So now, once we have that, for generic data, if we have one of these holomorphic curves, the boundary of it would be nowhere tangent to this xi, right? So it's somehow tangent vector everywhere, independent from xi. So we can use xi to frame the curve, and then once we have this, once we have this normalized this generic behavior on the boundary so that it's nowhere tangent to xi, then we can define this linking number by counting. So we say that linking between U and L is just the intersection number between U of S then in the interior times C. And that's well defined as long as we're not tangent to xi. So now let's see what happens when we become tangent to xi. Well, when we become tangent to xi at some kind of isolated moment, see, it looks like this. Here's xi, here's j of xi, but our curve is holomorphic. So near the boundary, this thing is also equal to the tangent of u of s, right? And therefore, as I deform this thing generically, I push it through here, then I would find some kind of intersection point here. And if I draw the top view of these, if I take xi to maybe point out of the board and then project in direction of xi, now everything became wrong color, but doesn't matter. So what we're seeing is exactly this. Here we have the tangency, and then after the tangency, we have an intersection. So this is in US intersect C, right? And this is exactly this relation that this guy is equal to A times that one. So this accounts for the A. So we see that if we now fix this 4-chain and do this business, then we have actually a deformation invariant count. Okay? So let me write down the deformation invariant count. So the theorem, and that's by myself and Vivek Shende, says that the Skein valued Kerr count Skein valued Kerr count, and what is it? It's somehow, maybe I call it Z of X and L is equal to the sum over all these things in the moduli space. And then I take, well, I have this number, and this is some transversely cut out orbifold thing, so it's some rational number, times Z to the minus Euler characteristic of S, A to the linking of U and L, and then take the boundary of S thought of as an element in the skein. So this whole thing lives inside in the skein of L, or actually some completion, is invariant.
Well, it would be great to see whether curve count can be valued in some other not invariants. For example, knots can have various very nice invariants, and one should see how well, and they can have cobordism invariants, and we should see how curve count can be valued in something even more powerful than curves. When count is not numbers, is not polynomials, but something more. Is it possible?
Well, somehow something should be possible, but so I should say, so in terms of other invariants, there is some kind of straightforward generalization that we never wrote down, but which replaces this Homfli Skein with the Kaufman Skein and some C2 invariants. But that's not what you have in mind. So let me try to answer what you have in mind. So one could imagine that you could lift these curve counts to some kind of Homfli homology level or something like that. This is not going to be an easy task. This is not going to be an easy task. So what we're showing here, the pictures that I'm drawing or the theorems surrounding them, is in some sense saying that the count of holomorphic curves with boundary is equal to this kind of Homfli Skein. So that means that if you would like to catch something like Homfli homology this way by counting curves, you need to have some more structure, maybe some kind of, what everybody would guess is some kind of S1 or U1 equivariant configurations, or somehow you pick some special complex structure, put the thing in some special position, something like that, right? So in some sense, what we're seeing here is a fairly clear connection between the curve counts on one side and the knot theory on the other side, the Homfli Skein on the other side. And if you want to upgrade one side, you sort of have to upgrade the other side as well. And one can speculate a lot about what it is. And I think this kind of super interesting problem, which I've been working some on, but I don't have any definite answers to how you actually lift this thing, right? As you're suggesting. So the short answer is I don't know, but I could talk about that for many hours. Why I don't know. Okay, but you need to do something more.
If we have just a count of curves, this
Yes.
means that we see how many curves. But if we want to do some homology, like Chobanov homology, we should see how curves interact. We should see how curves get transformed to each other.
Yes.
Yeah, and it would be yeah, extremely interesting to see. Yeah.
No, I agree. I mean, one should look at somehow some specific one-parameter families or all one-parameter families or something like that. But it's so. I mean, short answer is I don't know exactly how to do it. Yeah. There was
Okay,
another
thank you.
question.
It's related. One good question I was going to ask, since curve counting, you related to in counting intersection numbers. Intersection numbers have a sort of are associated with cup products in cohomology, I presume. So there is that relation to cohomology, and secondly, I was wondering if the whole thing could be approached categorically between the category of knots and category of what you're studying, an appropriate category.
So I understand the question. And I think this kind of category theory question that you're talking about, that's what I try to answer in a way that if you lift sometimes in this knot theory, we know how to categorify or lift this Homfley business to the next categorical level. On the geometric side and this curve counting, we don't know how to lift this picture, and it has to be, one has to add some structure or do something which I cannot answer in a good way that question. More than that, I think this is very interesting. It would be great to understand better how this works, and there are many kind of suggestions. You should count BPS states and so on, but the question is a little bit, what are they in terms of this counting? And it should be some curves collected together or something like that. But I don't know the answer to that right now. And as for cohomology and so on, here, so very often in this kind of Gromov-Witten and so on, you use the underlying topology of the Deligne-Mumford space to kind of cut down things and count not all curves, but some curves that basically parameterized by cohomology in there. And in that way, maybe some souped up version of these, if you could categorify, or you're interested in studying high dimensional families of these in the Calabi-Yau case, then there could be some input of that, right? That you have cohomology and moduli space. Other type of cohomology, like quantum cohomology or so on, you could imagine that you can do something like that here. In this literal case where everything is rigid, maybe not so interested, but if you go to other manifolds where you have to cut down moduli spaces to rigidify things, then certainly there should be some kind of cohomology products with values in this Skein as well, right? So we haven't developed that, but I'm sure that should be possible to do something, kind of tweak quantum cohomology as much as you can and take into account Skein valued things on the boundary. That's a great idea. That's something one should be able to do, but I don't know. Okay. Thanks for question. That's great. So, yep.
One more. How about relating it to the Jacobian of a curve? Would the questions you're investigating pass to the Jacobian in any sense?
That I don't know. I'm not so sure, but I don't know. So,
Thank
okay.
you.
Sure. So now we have this Skein valued curve count. So let me maybe try to get to this so-called Uguri-Waffa conjecture. So, and this Uguri-Waffa conjecture states basically the following. And that's a conjecture from 99. So what they say is that you start with a knot inside the three-sphere, and then you associate to this knot its conormal inside the cotangent bundle of the three-sphere. So this conormal, that's the set of points in the cotangent bundle where the coordinate sits on the knot, and P kills the tangent vector of the knot. So that means that this is topologically it's S1 for the knot, and each point of the knot you have two-dimensional space of vectors that annihilates its tangent vector. So this is an S1 times R2, and of course on this guy here, this we think of as symplectic manifold, and we take symplectic form is D of the Liouville form or action form, whatever you want to call it, dp dq. So certainly, so this p1, dq1, and so on. So certainly this picks the one q direction and the other two p directions. So certainly it is Lagrangian. So then they say, so then they shift off by one form, close one form, say d theta in tubular neighborhood. So every knot has tubular neighborhood. It's S1 times D2. And in this one, we have the one form d theta, and we can just shift the Lagrangian along d theta. It stays Lagrangian, becomes what's called non-exact Lagrangian. So it has some kind of flux. Integral of this PDQ form around the central S1 is no longer zero, it's something. So we shift it off, and then we perform the conifold. So I'll tell you about the conifold transition. So here I'm going to draw a schematic picture of T star S3. So this topologically at infinity, this is just S2 times S3, right? And here, if I draw it like this, then the S3 is alive, but the S2, I should draw it better. So the S2 here, it bounds at D3, right? But then I can imagine shrinking the S3, and I go to, if you know a little bit of algebraic geometry, this is just a quadratic cone in C4. And so here I shrunk them both, and then I can go out. This is this kind of deformation popular in string theory. I can go out the other way. So I can let the S2 leave instead. So at infinity, somehow topologically nothing happens. And what this space is O minus 1 times O minus 1 over CP1. So you see that we kind of go from an exact symplectic manifold, this T star S3, over on the other side we have local P1. So this also Calabi-Yau. And now I'm going to draw this Lagrangian. So the Lagrangian was sitting in here, and it was off of the zero section. It was shifted off by this d theta. And therefore, I can consider the same Lagrangian in this space, and it's also off from this central circle. And this Uguri-Waffa, they made I'm going to do the first version conjecture. It says that the count of curves So maybe I'll call this space the conifold, resolved conifold X. Count of curves of X inside L in LK inside X is given by say Z. So they of course didn't quite write this as Skein valued, but it's very close to Skein valued. Maybe I'll write it. It's the sum, and we'll prove it in this way. So, but it's the sum of Homfly polynomials, sum over all lambdas A and Q, or maybe, yeah, so Q, they write it in Q minus Q inverse is equal to Z, some change of variables from our count. So times, and there would be some kind of formal variable. But in particular, if we look at the first term here, so first term, that would be Homfly of K times just S1 times 0 inside the conormal. So let's look at these first, and let's do the other ones later. So they're claiming it's a kind of interesting thing, right? So we start from, and this was the first completely formalized conjecture in this way, right? But we start from knot theory. We take a knot, we count, we take its Homfly polynomial. What this is saying is take the conormal, shift it off, push it into the conifold, and then count the curves, right? And count the curves means that now A, so this CP1 is somehow the logarithm of A, right? So we counting curves in certain homology classes, and A tells us in which homology class we. So we get this enumerative interpretation, and this was for a long time. It's been since 99 somehow used a lot, but it wasn't proved, and there was not even any kind of real indication of proof. But from this Skein counting, we can actually prove it. So let me prove it first for this first term, and then I'll discuss the rest after this. So here's the proof. I'm going to draw a slightly weird picture of this conormal, but sorry. So here we start with the Lagrangian, and then inside this Lagrangian we have the knot, right? And I'm going to draw the conormal of the knot in blue in a funny way. So I shifted it off, and I'm going to draw the R2 people like this. So you see this one of these parabolas, that's an R2 in the conormal. So here is LK. I shouldn't say L, I should say S3. So the picture that I'm drawing is in T star S3. It's S3, and all of it sitting in T star S3. So now it's easy to see, because if I take this very small shift, I can even introduce complex coordinates near this one. So it's very easy to see that there is exactly one holomorphic annulus stretching from the conormal down to the zero section. There's no other curve. This is somehow elementary. So let's now do the Skein valued count in this homology class, the things that go once around the conormal. So we do the Skein count. So Skein count. So what is it? It's 1 for this annulus, and then it's Z to the Euler characteristic of this annulus, which is 0. And then it's A to the linking, which we can set up to be 0 as well. And then finally, it's the boundary of the annulus in the Skein. In the Skein of S3, so this one should now live in the Skein of S3. That's one of the boundary components. Tensor the Skein of LK. And what it is just, so it mostly is 1, then it's the value of K, that's the boundary, this is K, right? is the value of k in S3, so it's the Homfly polynomial, tensor this S1 times 0. So the S1 times 0 just stays. We can't do anything. It's just a generator of the Skein module. Okay, but this is equal to, as we said, it's just a Homfly polynomial of k, variables a and z, and then in the Skein, and then times this S1 times 0.
Excuse me, I missed a couple of minutes. So are you proving some partial case of Oguri-Wafa or what?
I'm proving the general.
The general. Okay.
Yeah.
The
But
general.
I'm
Okay.
starting, so Oguri-Wafa says something about many curves going any number of times around. But that thing is easier to understand when we go completely to the Skein counting world. So I'll do it soon. But I'm starting with proving the first term here, which is just saying that the curves that go once around the conormal, they should count the Homfly polynomial of k. Okay?
Okay.
So I'm doing only that one first. And I first, and I now did the, so I did the count now in T star S3, okay? And now I'm going to transfer this count by a trick known as SFT stretching. So, maybe that was wrong color. So I'm going to take a smaller, so there was some kind of shift here, let's say delta. And so I'm going to take a very small neighborhood of the zero section here of size epsilon. And then I'm going to deform the complex structure here. I'm going to use the deformation invariant, so-called SFT stretching. So symplectic field theory stretching. So maybe I'll draw the picture again and say what happens under this SFT stretching. So this is our conormal. Sorry. Okay, here it is. And then we have some kind of curve that goes off from this conormal. And when I do SFT stretching, this curve breaks into pieces which are inside and outside this kind of epsilon neighborhood. So, and these pieces are joined at so-called Rabe orbits. And then they go down to the zero section. So here is somehow this, in here is T star S3, and out here is somehow unit cotangent bundle of S3. Whatever is called T star S3 times R. And then there is again somehow basically the same as this Riemann-Roch form that says that these are Rabe orbits of some contact form, but we can take the contact form of the round metric. So they are the same thing as geodesics, or the round metric. And the index, the input in dimension formula of these ones are the same as their index as geodesics. So that means that everybody here has dimension input less than or equal to -2. So in other words, this outer piece, if at all there's any piece inside, this outer piece would have dimension less than -2. And that means that for generic data, it's not going to happen. So this implies that for generic data, so here would be, say, J, generic stretching, the curve leaves, or all curves leave in the neighborhood. So what we find is we find this kind of same thing again. We find this conormal, we find the knot in here, and then we have the zero section here. And then the curves actually do not touch the zero section anymore when I stretch sufficiently far. So they all kind of became closed at that end. And now we know the count is invariant under such deformation, right? So count is still equal to the Homfly of K, A, and Z. And now A, contributions come only from A to the linking of U and S3 and Z to the minus Euler characteristic of S, right? So that means that now it's a kind of a more honest curve count. There's no input from knot theory. Knot theory is empty. And so now if we go back, so this now happens, this blue thing, everything is in T star S3 minus S3. And if we go back to the picture, we can just say that this is the same thing as this X minus CP1, and we can fill in small CP1 without changing curves. So then of course, one has to prove this, but somehow once we have the curve off of the zero section, it's not so difficult, and that somehow is this proof of the first step in this Guri-Vafa conjecture. And so yeah, so that's the proof. And so I'm now kind of out of time, but let me just say something about general case.
Excuse me, you are not out of time. Usually we have an hour and a half.
Hour and a half, okay. And then I can continue a little bit. I'll continue with this with the full Guri-Vafa then. So full Guri-Vafa. So what one first can show is that in this case, we want to do the same thing. And one can show that all the curves, so all curves are multiple covers of this annulus. Okay, so as you know, you could have kind of these covers, and they could be branching and whatnot, right? The problem with all these branch covers and all these things is that on the one hand, maybe they are not, some of them are actually rigid like curves, right? So maybe not all of them. So that's one problem, they're not rigid. And the second problem is that even if they're rigid, they are just not knots on the boundary, right? If you take a 15-fold cover of this annulus, it's just going 15 times around, right? And the knot that is drawing is 15 times K, right? Which is not really a knot. So it's an immersed curve which is not embedded. So the question is now, what is the contribution in the Skein valued curve count from this annulus? That's the thing that we need to know. If we knew it, then we would be in business. So let me explain. So we need to determine the contribution in the Skein of L. Let's say. Okay. So in order to do that, we move to a local model. So I'm going to study another local model which will allow us to calculate this contribution. So near this node, everything looks like the local model that I'm now going to tell you about. So new local model. So we take T star S1 and we multiply it by C2, okay? And in here we have L0, which is S1 times, let's say, R2, and we have L1, which is S1 times, let's say, IR2. So these are transversely intersecting Lagrangian, intersect along the knot, right? And so I want to include this shift. So let me do that. So I'm taking S1 times, shift it up by epsilon in this kind of T star S1, and then times IR2, okay? So here, as you see, we have this kind of model. If I draw, so if I first draw this kind of T star S1 thing here, it looks in this direction, it looks like this is L0 and this is L1. And indeed, I have this, my favorite annulus and maybe all its covers. If I draw in the other, in the C2 directions, it basically just looks like this, right? So this is R2 and this is IR2. So it's easy to see that in this picture as well, the only holomorphic objects there are the branch covers of this one, because anything is invisible in the C2 directions, okay? So now we are going to calculate, using this Skein valued thing, this number of curves by using a nice trick. So the idea is we use curves at infinity. So we now need to understand what do these L0 and L1 look like at infinity. So it's not so hard to see in this case, because somehow the S1 direction is not so relevant. And in the C2 direction, we see that if I draw kind of a very large sphere here, it's an S3. And so now I need to understand how these things end here. So it would be S1 times this one-dimensional Legendrian link in S3. And that Legendrian link, of course, is well known. It's the Rabe shift of the unknot or something like that. So at infinity, the Lagrangians DL0, DL1 form a Legendrian Hopf-link times S1. Okay, so if I draw it in the local, I can push it in the local patch, and then it just, so I have kind of contact form dz minus y dx, and if I project it to the xy plane, what I see is I see this picture. And then times S1. So now we see here, this is a projection, but we have some kind of, we have Rabe chords, and we're going to call it C1, C2 for these two crossings, and maybe B1, B2 for these two crossings. And in this case, what we're now going to observe is that if we can understand the curves that are at infinity, then we will get some kind of recursion relation for the Skein. So let me tell you about that. First, let me draw these curves at infinity. They're not so hard to find in this case. So really, it's a kind of Botmore situation, but what it comes down to is finding the curves in one of these slices. That's enough. So and they look like this. So you have this curve. There's one disk. And then you have this curve, there's another disk, and then you have two triangles, and I'm going to draw one on the other side in blue here. So this is the triangle which goes down, jumps over here. So this is somehow picture well known in this kind of study of Shikhanov-Ilyashberg algebras or whatever. So of course this is not the first time these holomorphic curves appear. But this time we should draw them and think of them in the following way, that we have here at infinity three curves, some curves looking like this. So we have three of them on each Lagrangian. So this is the first one, and maybe minus the second one, and then plus or minus this guy. So this is on one. This is also on one. This is on one, but this boundary here is on two, right? So that's the triangle on one. Maybe I'll draw a new one. So we have the following picture. I have two curves with boundary on one, and this is kind of C1, C1. I have this triangle, C1, B1, B2. This is on 1, this is on 2. And then I have another one, which is on 2. So they're kind of similarly looking curves, but they are on 2 instead. Maybe plus. And then I have some other one, which swaps these ones. And I have C2. This is on 2, and this is on 1. Okay, so now we want to look at the moduli space of all the curves that have, say, positive puncture at C1, right? So I'm going to call that moduli space C1. And when I say all the curves, I want to look at, so maybe I'll move this a little bit. Okay, so when I say all the curves, what curves do we have? We have those at infinity. This is a one parameter family of curves, but I have to look at all disconnected curves. So I also have this kind of annulus person inside here, and I'm going to call the count of those Z. Of course, here as well, and here I have that thing as well inside, but then I may have, I'm going to draw it in blue perhaps. I may also have some kind of curves going off from here. But the point now is that the boundary of this moduli space must be 0 if we count it in the skein. This kind of skein boundary is 0 because it's a one-dimensional manifold and its boundary is 0. So if we think about it, maybe we start here from the first one, we push down, we start intersecting and skeining and whatnot, but all this intersecting and skeining is not boundary. That's the whole point of skein-valued curve counting. So we skein away, and the only possible boundary we have, the curves that go off to infinity. So they are shown here. So that means that the sum of these three terms has to be 0. And if we now look at the second equation, which looks very similar, note that it's the same kind of curve that you have to attach here and here. So we have a similar equation here.
Excuse me, am I right that in some situation you can make some legendrization of knot theory and whatever else? I mean, from just a classical topological object by using some tricks, you get a Legendrian objects, and maybe instead of numbers, we can dream about getting something like Chicana-Ashberg TGA.
Yeah, you could do that sometimes, but Chicano-Ashberg DGA here is so in this setup when you have these tori at infinity, Chicano-Ashberg DGA is somehow genus 0 version of what we're doing now. So we're doing a vast generalization of Chicano-Ashberg DGA. So this is full genus version of Chicano-Ashberg DGA. So if I just looked at disks in what I'm saying now, then I would do something with Chicano-Ashberg DGAs. I would compute some disk potential. But now I'm computing everything with some kind of generalization of this Chicano-Ashberg DGA. Okay, so now you see that if we add these two, if we first pick the right kind of paths here to close things up, so that this guy here matches this guy here, and that guy here matches this guy here. So that determines these paths. Then I could sum these things, and what I would find is the following equation. So if I write up, remember what these curves, they were kind of going one way around, the other way around. So I'm going to write now an equation and explain in a second. So I would find P10 on 1 minus P00 on 1 acting on the Z has to be equal to P10 on 2 minus P00 on 2 acting on Z. So this P10 and so on is somehow, these are tori, and P10 is just meridian, and this P00 is an unknot. Okay, so I get this recursion relation, or I get this relation that shows that these very easy operators, they have to annihilate the partition function Z. So whatever the count of all these things are, they have to be killed by this Z. And now some facts about this Skein. So Skein of S1 times R2, or maybe I'll say positive Skein, is equal to, it has a basis, as eigenbasis of operator P10. So what I'm saying, if you have a solid torus, you take a link inside there, you can surround it by a meridian very far out. That gives you a new link, and if you think about it, you can kind of skein away this extra meridian, and you can hope to get some kind of eigenvalues, eigenvectors and eigenvalues, but it turns out that this Skein, positive Skein, has an eigenbasis of this operator, and it's somehow W lambda, where lambda is a partition. So in other words, you can think of it as a Young tableau. And they have distinct eigenvalues. So we learn from this. So then this operator equation So actually, to be completely honest, now you see that, well, gives that Z in this case is equal to just the sum over lambda of this W lambda tensor W lambda. So W lambda on one tensor W lambda on the second one. So you see that because these ones have to be equal, we have to get something like W lambda tensor W lambda 1, 2 times something. It has to be on the diagonal because of this equation. And this something is not uniquely determined by that. You can determine by some trick. But if here it's even better. So you can actually compute. You can compute the blue. And when you do that by some flow tree trick, then you get unique solution. It's just determined. And you can show that the solution is this. So now, if I kind of skip back to this Oguri-Waffa. So for Oguri-Waffa, so what we had, so there was this kind of conormal. Here we had this thing, and now it's coming down to S3. And now we know that if I go for all these ones, this one would be sum over lambda W lambda tensor W lambda. So that means that the count of this LK in T star S3 is equal to sum W lambda S3 tensor W lambda LK. And now that one we can say is equal to sum over lambda, Homfrey polynomial of, by definition if you wish, Homfrey polynomial of not k in lambda, and then tensor this W lambda LK. And then you transfer these to the resolved conifold in the same way, and you find now that this one is somehow really curve interpretation of this count, because there's no lower boundary anymore on S3. So it's the same thing. So once we find this, once we find this local contribution of an annulus, you can do lots of things like that. So I think I'm going to stop at this and take questions. So thank you very much.
Okay, thank you very much for a great talk. Are there any questions or comments? So there was something on the chat, I guess.
Yeah, I somehow had some problem seeing the chat. You should unmute or something. Let's see. Did we hear?
Yes, please unmute.
Yes. Okay, maybe not.
Okay. I think I will.
You disappeared. Oh, now you're back. And now you should unmute.
I think I will look at your talk again, and maybe we may organize a discussion because I have a lot of questions.
Okay.
Okay. Thank you very much. It was really great. Yeah.
Thank you. Thank you. It was a great pleasure.